Assalamualaikum and selamat sejahtera. I'm Amin and you are now on my YouTube channel Discover Geophysics. Thank you very much. If you have already subscribed to my YouTube channel and if you haven't subscribed it yet, please click the subscribe button below now. Inshallah, if there are any beneficial videos, they will appear in your YouTube feed. So we are back in the topic of gravity data interpretations, and I believe we already covered some part of it. To recap, we have learned the fundamental of gravity, including the universal law of gravitation and some related theories like relativity of Einstein's. However, the most important aspect is the applications of the gravity to geology and how gravity responds to geological features. Over this again. The final products of gravity survey are either the complete Bouguer anomaly, or free air anomaly. Since the free air anomaly is mostly suitable for the offshore studies due to the lack of topographic variations, the complete Bouguer anomaly is commonly used for onshore interpretations. Onshore surveys require analysis of elevations, topography, and slab mass effects to ensure the gravity anomaly data is as accurate as possible. These three final products consist of a range of frequency and can be separated into different categories, typically high and low frequency. Before moving into the details of frequency analysis, let's examine the method of gravity data acquisition so that we can understand the theory, the fundamental behind the frequency separations. Gravity data acquisitions can be conducted through either profilings or mappings. Let's go to the profiling first, or a single line survey. So this type of survey involves a series of gravity stations across different types of lithology. For instance, a single lines survey with 6 gravity stations has been conducted across the two types of lithology, limestones and granite, with density of 2.7 and 2.4 gram cubic centimeter respectively. So this study is purposely to observe their responses to gravity measurements. A graph of Bouguer anomaly on top is then produced to analyze the responses. Typically, rock with higher density will exhibit higher gravity anomalies or vice versa. With a multiple lines of gravity survey, we can map the study area to produce a Bouguer gravity anomaly map. This approach allows us to interpret the geology of the study area in greater details, considering factors that might affect the gravity reading, such as unconformity, faults, and other geological features. From this figure, we can observe the gravity response where lower density rocks shows lower gravity anomaly, while higher density rocks shows higher gravity anomalies. The yellow region, which is display a moderate range of gravity anomalies, can be identified as the lithological contact between the limestones and the granite. Once more, the resultant data comprises both high and low frequencies. To understand this concept better, consider this example. The image shows the subsurface containing a shallow ore body with higher density with 0.5 GCC and a deep-seated granitic basement with lower density, which is 0.2 GCC. The profile of the Bouguer anomaly illustrates the response of both ore body and the basements. Without the ore body, the response would be simply follow the trend of granitic basement, which is tilted to the right. However, the presence of the ore body deflects these trends. Therefore, the data obtained from the gravity survey may reflect influence from both shallow and deep subsurface layer. Lacking prior knowledge about the geology of the study area could lead to misinterpretations based on numerous assumptions. The assumptions regarding subsurface condition can vary and are often constrained by our knowledge of the study area. Therefore, we need to examine both the shallow and deep subsurface trends. Since the data contains responses from both shallow and deep sources, we must separate them. However, these separations can only be achieved in the frequency domain. So the data that we acquire, that we obtain, is in spatial form, meaning it depends on distance and times. To convert the data into the frequency domain, we need to apply or employ a frequency transform called Fourier transform. These transformations convert spatial data into frequency domain, revealing low and high frequencies, corresponding to long and short wavelength respectively, as shown in the graph. By applying low pass filter, we actually eliminate high frequency while retaining low frequencies. Small bodies in the shallow regions remain unaffected by the low frequency filter due to their resolutions, allowing them to just pass through. So no effect much on the shallow part. So additionally, they possess the ability to penetrate deeper with minimal energy attenuations. Consequently, the result shows only the trends of granitic basement as shown here, while removing the shallow regions. So this product of the low pass filter is always referred to as the regional anomaly. In contrast to a low pass filter, a high pass filter operates differently. It removes a low frequency while preserving high frequency. With their short wavelength, the high frequency components carry energy predominantly in the shallow parts, making them more sensitive and providing higher resolutions. The high pass filter captures shallow geological features but lacks the ability to penetrate the deeper layers or deeper part. As a result, only anomalies associated with shallow features, like for this example, ore bodies, can be detected. So this product of the high pass filter is referred to as the residual anomaly. Broadly speaking, whether it's the Bouguer gravity anomaly, complete Bouguer gravity anomaly, or free air anomaly, they essentially includes the combinations of regional and residual anomalies, indicating both shallow and deep features. This image shows the Bouguer gravity anomaly of Kedah, Malaysia. Generally, the gravity anomaly correlates with the formations and lithological characteristics of the study area. After low pass filter is applied, this is how the regional anomaly map is look like. So basically, regional anomaly are recognizable on maps by their smooth contour lines, parallel arrangement, consistent spacings, and significant magnitudes. These characteristics stems from the relatively undisturbed nature of the deep subsurface, with fewer structural features. So geologists and geophysicists frequently utilize regional anomaly maps to explore deep-seated features such as basement orientation, basin geometry, deep-seated fault, large anticline or petroleum trap, and also crustal structure. On the other hand, residual anomaly map display a complex contour lines, irregular patterns, uneven spacings between contour, and smaller magnitudes. So these features result from shallow structures of being subjected to various structural and tectonic event or tectonic activities over time. So geologists and geophysicists often rely on residuals anomaly maps to investigate the shallow structures like buried karst formations, small anticlines, cavities, and even for mineral exploration purposes. Before we go in detail about gravity data interpretation, we must understand that the gravity outcomes are non-unique and ambiguous. Non-uniqueness refers to that the fact the multiple different subsurface model can produce the same gravitational field measurement. This is because gravity data is an integrated responses from all masses within the subsurface, meaning different mass distributions can yield identical gravitational anomalies. For example, the illustration shows that the response of gravity anomaly of an area. The source of response could be from many possibilities, either from long, shallow, weak density body that thickening at the center, or it could be a prism moderate density body at the middle, or it could be a strong sphere mass at the deep part of the subsurface. Ambiguity in the gravity method arises from the difficulties in distinguishing between different geological scenarios that could explain the observed gravity anomaly. That is related to but distinct from non-uniqueness. Ambiguity involves multiple reasonable geological interpretations rather than purely mathematical solutions like non-uniqueness. For instance, the gravity response might result from a single source body in scenario 1, or a stack of several source bodies at varying depth and sizes, or maybe different materials with different density as shown in scenario 2. Both scenarios shows the same or maybe the cumulative response from multiple bodies. The scenario could be even more complex with different arrangement and possible subsurface situations. What is crucial for interpreting gravity data is the depth of our geological knowledge of the study area. It is advisable to have a visit to the field so that we can have a clue on some possible scenario. Okay, now let's proceed with the gravity data interpretations. In general, the gravity data interpretations can be divided into qualitative interpretations and also quantitative interpretations. Qualitative interpretations of gravity data involve descriptive and conceptual understandings of the fundamentals of the gravitational anomalies and their geological implications without extensive numerical analysis, like quantitative interpretations. It will merely focus on identifying patterns, trends, and general characteristics of the gravity fields. Most of the time, geophysicists observe and evaluate the gravity responses based on the anomaly attributes like amplitudes and its wavelengths. For example, the response of the same source body is depending on the depth of the same body. Shallow body will give high response of anomaly but lower response of anomaly if the same body is situated at the deeper part. We can have a preliminary data interpretations or any idea first when we look into the data. The key aspect of qualification or qualitative interpretations includes number one, anomaly identifications, geological mappings, and regional trends. For anomaly identification, recognizing the characterizing gravity anomalies such as positive or high anomaly or negative low anomalies, which may indicate denser or less dense material respectively. And we can expect the orientations of the sources by the way they're presented in the anomaly graph. For example, here, the response of the various angle of tilted dike or vertical dikes like 90 degrees, 60 degrees, or 30 degrees affects the way the anomaly graph is presented. Geologists and geophysicists frequently correlate gravity anomalies with known geological features such as fault, faults, and lithology boundaries. For instance, the Bokbak faults in the Kedah can be identified by the dance of the gravity anomalies separating high anomalies region with low anomaly regions. Difference in gravity value can also distinguish granitic area in the red circles from the sedimentary areas in the green circles due to the variations of the density of the lithology. Geologists and geophysicists often use gravity surveys to examine regional trends, helping to infer large-scale geological structures like sedimentary basins or mountain ranges. Gravity surveys are typically used as a preliminary step before more detailed or focused study is coming, like seismic survey, so that we can understand the regional trends before we apply a more focused study. And then we also can study about the geometry, the structure of the study area in general before we go a detailed study. This approach helps to avoid unnecessary planning that would cost us a lot of money, could cost an amount of money like $1 million that we're going to waste. So this is very necessary step before we go with the focus study. For example, I give you an example here. In the provided image here, there are 3 major sedimentary basins that can be identified here at offshore of eastern Peninsula Malaysia based on low gravity anomaly here, the blue color one. They are the Malay Basin, the Penyu Basins, and the West Natuna Basin. Most of our economical viable oil and gas extraction come from Malay basins, while the Penyu and West Natuna Basin are still under study. So we have a chance in the future for Malaysia to grow its economies when the geologists or geophysicists explore at these 2 areas in the future. Now we move into quantitative interpretations. Quantitative interpretations involve the numerical analysis of gravity data to create a detailed and precise subsurface models. It uses mathematical and computational techniques to derive physical properties and geometrics of subsurface structure. In fact, the anomaly frequency separations for regionals and residual anomaly that we have discussed just now is also part of the quantitative interpretation. So the key aspects in quantitative interpretation always involve either forward and inverse modeling and also parameter estimations. So we look into the forward and inverse modeling first. So forward modeling is creating theoretical gravity model based on assumed subsurface structures and comparing them with the observed data. So we have calculated data and the observed data. We will explain later. And then inverse modeling later is using observed gravity data to infer the distributions of subsurface density, and it is always often through iterative computational algorithm. Forward modelings often involve creating a profiles like this one. Okay, by using general density inputs. So we're going to input densities into our calculated data in order to construct a calculated models. So the primary objective is to align the calculated data, the continuous line here, with the observed data represented by the dotted line here. So this process allows us to model the subsurface based on the input model and the observed data. Okay, and then we're going to have several attempts so that it will try to imitate the actual as possible the subsurface of data. Constructing an accurate models requires experience and a deep understandings of the geology in the study area. Otherwise, the resulting subsurface model may be inaccurate or useless. And then inverse modeling. So inverse modeling, as mentioned, we need to have some algorithms involved in the calculations, and this is how inverse modeling is frequently being modeled, and is frequently used to understand the distributions of the subsurface density and can be applied in both profilings and modeling, and most of the time we apply inverse modeling for the 3D. So this approach is basically helpful for investigating the lateral and vertical distribution of subsurface density and the density value extraction, thereby enabling more accurate interpretation of the subsurface. Now we move into parameter estimations. The half-width method is the quantitative interpretation that is well-known technique for parameter estimations. In gravity interpretation, it is a simple and yet effective method used to estimate the depth to the top of buried geological structure that produce a gravity anomaly. This method is particularly useful for a quick initial assessment and involve minimal computational effort. Typically, the half-width method is applied to either Bouguer anomaly or residual anomaly data, where the amplitude is more pronounced. So the focus is on the specific sections of the gravity anomaly to estimate the varied geological structure. So how we do the interpretations from this half-width method is first, we need to identify the maximum value of the gravity anomaly. For example, here in this case it is 34 milligal roughly. Then we need to calculate the half amplitude of the anomaly, which would be 17 milligals. So next we need to identify the points on either sides of the anomaly peaks. Okay, we need to project it to the right or to the left of the anomaly peaks where the amplitude equal the half amplitude value. Okay, projecting either to the left or to the right. Lastly, we need to measure the horizontal distance between this point. So this distance is then used in a specific formula to estimate the depth of a buried geological structure from the surface to its center. For instance, using a half-width distance of 5 kilometer, the result that we obtain here. So the formula can be varied slightly depending on the shape of the body as shown over here. For example, here we have horizontal cylinder. So this horizontal cylinder is more straightforward, where the result is 1-to-1, meaning that the data that we obtain from here is directly, we can say that the Z ataupun the depth of estimation for the body at the center of the body is roughly less than 5 kilometers. Okay, if spherical body, then we need to multiply with 1.305 as shown here. So that is how we do it. Depends on the estimate simple body features on the subsurface. Okay, now let's have another example of the half-width method explanations for parameter estimation. If we know that the geological body is a vertical cylinder, for example, such as a buried dike column, we then need to multiply the outcome, which is the 5 kilometer, by 1.732. So this gives us a depth of 8.99 kilometer from the surface to the center of the dike column, for example like this one. However, it is important to recognize that this method has significant limitations. The limitations are simplified assumptions in terms of resolutions, and lastly anomaly overlaps. So let's take a look on the simplified assumptions. So this method assumes simple geometries which might not represent complex subsurface structure accurately. For example, the equation that I showed you just now is only for simplified model. It's a perfect sphere. It's a cylinder. It's horizontal cylinder, vertical cylinder, and flat body, something like that. So it's not really representing the actual part, but we can do the estimation based on our understandings of the study area. And then we take a look on the resolutions. So the resolutions, in terms of resolution, it provides an estimate of the depth to the top of the body, but not its full shape or size, because we only can detect the roughly the depth from surface to the center of the body, not really exactly the shape or the geometry of the body. And then it's also lastly we have anomaly overlaps. So in areas with multiple overlapping anomalies, identifying the half width can be challenging, okay, because the anomalies not just come from a single body, but due to the many stacking or numerous overlapping anomaly. So our estimations of depth of the body might be wrong or inaccurate due to this overlapping problem. We are now reached the end of our session for today. To summarize, each of the three final products consists of a range of frequencies and can be separated into different categories, typically high and low frequencies, that will produce regional and residual anomalies, revealing the deep and shallow subsurface respectively. Gravity interpretation can be approached qualitatively, providing a general overview, while a focused study of the subsurface involves quantitative interpretations. Don't forget about the half-width method, even though it's not really accurate, but that is one of quantitative method that we should consider for the future study. And again, before we conclude, I invite all of you to subscribe to my YouTube channel for additional insight and update. I hope that this video will furnish you beneficial input for your study in the future. That's all for 25 minutes. With that, thank you very much and see you all soon.